Hello everyone, this is Stefan Nessmann and it is my pleasure to welcome you to our first video lecture for the course Advanced Data Analytics and Management Support. Today I would like to share some background information on this module with you. Information concerning, for example, logistics, how we will organize the course in the summer semester 2020, and we will also look into some, real-world use cases of these data analytical methods that the course is all about. I hope you will like this video and let's just get going. So here's the agenda. We'll start with some introduction and background, then dive into course logistics and revisit some business applications of analytics and data science. Now, starting with the introduction, let me tell you a little bit about the background and the history of the course, just so that you understand how it fits into the teaching offers at the Chair of Information Systems. Here we have our teaching offers, at least those for the master curriculum. And I trust many of you will have taken the course Business Analytics and Data Science in the last winter term. Now, I get a couple of questions whether completion of that course is actually mandatory in order to participate in this course. By the way, I will in the following abbreviate it by ADAMS, Advanced Data Analytics for Management Support, or ADAMS. Now, is it necessary to have completed the BAD schools prior to ADAMS? No, it's not strictly mandatory. It's useful for sure, and I strongly recommend it because we will draw a lot on the concepts that we have covered in business analytics and data science. The functioning of standard machine learning algorithms, say random forest or boosting. The way we use these algorithms, for example, in a standard modeling pipeline, including parameter tuning, including cross-validation, how we judge the adequacy of algorithms using measures like the AUC, etc., we will just not have the time to revisit these concepts, but we will need them a lot, basically in every session of ADAMS. And so it is important that you are familiar with these concepts. And BADS is meant to give you a good basis for this more advanced course. But if you haven't taken BAD but are ready to, catch up, that's perfectly fine with me. Or if you haven't taken BADS but you have just done data science and you've done machine learning in other courses, on the job, wherever, and you have the basics, that's equally fine. So just, stay tuned, follow along the lectures, and if you realize at some point that you need some more background in order to follow, then it's maybe a good idea to just stop with it, take BADS before, but as long as you're okay, that's perfectly fine. So everybody is welcome to join this course. And you see it's the second lecture in our curriculum. And indeed, it's really meant as an extension of business analytics and data science. An extension in two dimensions. On the one hand side, we did not look into the processing of unstructured data in BADS. All the types of applications we've been looking at and the types of data sets we've been analyzing were, strictly speaking, well-structured data set, tabular data. But nowadays it's important to also deal with unstructured data, which, by the way, I will define in a minute, so that learning about techniques in order to make sense out of unstructured data is very important, and it's a key learning objective of ADAMS. And on the other hand, one very popular type of machine learning method maybe I could say the most popular technique these days, or at least one of the most popular techniques, artificial neural networks, we have deliberately left out in business analytics and data science. I have not covered them at all because I do elaborate on neural networks in Adam. So these are the key two extensions that we are going to explore. And speaking about artificial neural networks and deep learning, let me briefly comment on one of the other big terms that are all around these days, namely artificial intelligence. It's probably the buzzword of our times, very trendy term these days. AI, now what is AI about? Let's briefly revisit that. By the way, AI is nothing new, really. AI is a field that has been around in computer science for decades. You see the very, first notable result I'm referring to on my slide here dates back to 1946, the first programmable electronic computer by SUSE. And you see some other milestone on the slide here. We have 1997, for example, where IBM's Deep Blue system was defeating the world chess champion Garry Kasparov. These are the early days of AI. Very recently, we've been experiencing some major breakthroughs, which on the one hand side really already found their way in our daily lives. I'm thinking about intelligent systems like Amazon's Alexa, like Siri, or other forms of these digital assistants. And we had some more very notable and well recognized achievements by computer systems performing tasks that were not deemed possible before, such as winning Jeopardy against most successful contests, or very recently in 2016 Google's AlphaGo beating Lee Sedol in Go, which is a very complicated game, and as I said, it was not considered possible for a computer system to ever beat a world champion, which the system did in 2016. These are some of the breakthroughs in AI. What we see nowadays is big hype, virtual personal assistants becoming more prevalent. That would be one forecast, a near-time forecast. Obviously, you have heard about autonomous driving and the sensors that autonomous vehicles entail and how the signals coming in from all these sensory data are processed by computer systems with some form of artificial intelligence to make sense of these signals that come in and then adapt the driving of the vehicle accordingly. And certainly we have robotics, robots for manufacturing that will probably be very common in factories in 10 years from now, or a bit longer maybe. So these are only some of the examples where we expect AI to make an impact. And what we clearly see these days is that companies invest a great amount of money into the development of AI technologies. So some really significant activities going on right now, as well in the methodological space. Think about advancements in the scope of deep learning, and we see these sizable investments by many companies. We're seeing some frameworks coming out and open platforms and databases to further support the development and AI. And a very interesting development from an economical perspective is that we observe big IT players like Google, Apple and others to move and transit into more classical types of industries. And again, autonomous driving being one of the examples where these IT companies are the ones who develop the systems making sense of all these sensory data coming in to the autonomous vehicles. So very big, very colorful field, very hot these days. How does this relate to our course on advanced data analytics? The interface really is deep learning. Let's try to untangle that a little bit. I put three terms here on this slide: artificial intelligence, then we have machine learning, and we have deep learning. And so just in a summary, AI in general encompasses technologies that enable computers to mimic human behavior in its broadest sense. Mimicking some sort of human behavior. That's AI, the big overall field, the very big picture. And I trust all of you are familiar with machine learning. Much more narrow perspective, but a very important branch of AI. In machine learning, we explore systems and methods that aim at learning to perform some task without being explicitly programmed to do so. To provide you some context, historically, whenever you wanted a computer to perform some task, it was necessary to program this process, to program specifically what the task entails and what you want the computer to do. And with many real-life problems, that is somewhat difficult. Programming or descripting the logic, the steps to perform a task in a structured, programmable manner is not always easy. Let me give you one example. Imagine you want to program an algorithm that is able to detect an address. Say you want to do some character recognition, you want to automatically process invoices, and one of the subtasks in processing invoices automatically is to recognize which part of the invoice displays some address, like the address of your business partner. I mean, we do know that pretty much every type of address somewhat starts with a name. Well, maybe then names occur multiple times: name of a person, name of the company this person is affiliated with. And then we would have something like address information, which can be street plus zip code, but could also be somewhat different, or just imagine the different ways to depict a zip code on a global scale. And then we have a country code. In a nutshell, addresses come in many forms. And, programming this rich flexibility of what can actually represent an address, that's a pretty tough task, But on the other hand, much data is available from past invoices, for example, how addresses can look like. And this really is this is a job that machine learning might be able to perform. You show to the system a bunch of examples telling the system, look, this is an address, and that is an address, there's also an address, and then you let the system figure out rules automatically what makes up an address, so that the system will be able to recognize addresses on subsequent documents that you feed into your system. That is machine learning. And that is very much what we talked about in BETS for basically a whole semester. Now, deep learning is a specialized area within machine learning. The focus of deep learning, and maybe I should say in my opinion, is the ability to automatically extract features from data. I trust you're familiar with the supervised machine learning framework. If you feel a bit shaky here, just go to Wikipedia, search for supervised machine learning and read up on that. But you should better know that, right? In machine learning, we need features, and features used to be handcrafted. For machine learning algorithms to do a good job at, for example, detecting patterns such as what is an address, what is not an address, giving an invoice, we do need some good predictive features. And the promise of deep learning is that we don't need to handcraft these features, but let the algorithm figuring out the features automatically. That is the big promise. And that's maybe something to take home, what deep learning is about. To be really honest, my drawing here is maybe a little bit subjective. I could imagine that some colleagues of mine would prefer the slide to look somewhat like that. See my point? On my slide, I'm making deep learning a subfield of machine learning. I'm pretty sure deep learning scholars and enthusiasts are around who would deny and disagree with that view and say, no, it's actually a field in its own right, and it goes well beyond what machine learning is about. And hence, my drawing, if adopting that view, is somewhat inaccurate. Should be like that. Well, I don't want to spend too much time on definitions today. Just bear in mind that this opinion might exist as well. The key feature of deep learning I'd like to highlight is that of learning features automatically, and it's clearly something that distinguishes deep learning from machine learning. To give you an idea what automatic feature learning is about, it's been developed very much in the scope of image analysis. Images are composed of individual pixels. If you see an image of a computer, that's just a rectangle made up of a large number of pixels. Such large number that our human eye is enabled to tell the pixels apart, and this is how we see a picture. But actually, this picture that we see on the computer screen is just a set of a large number of pixels, each of which has its own color, for example. If it's a colored image, then we would have different color channels for each pixel. And the pixel, in that regard, is the most basic type of pattern in image data. But when we talk about images, for example, the image of a human face that might be shown in a picture, that has quite some complicated shape and pattern. And what this slide is meant to show, that from the raw pixels that make up an image, a deep learning model would function in a way such that some parts of the model would start to recognize basic patterns. Basic patterns like edges, for example, or squares, or triangles. And then other parts of the model, deeper parts if you wish, they would draw upon these basic patterns, edges, and begin to realize more complicated patterns, maybe the shape of a human eye, or the shape of a mouth or a nose. And then yet deeper layers would learn to make sense out of these higher level patterns and start to learn that when we have a pair of eyes and a nose and a mouth, then very likely there is a face in an image. So the very deep layers would start to recognize faces. And this kind of task sharing, first learning basic patterns, then aggregating these to learn more high-level type of patterns. That's underneath deep learning, or the idea of learning features automatically. And if you compare that to machine learning and you want to build a system that detects faces in an image based on machine learning, your task will be to come up with predictive or discriminatory features that describe how a face looks like. And you can imagine that this is non-trivial and more efficient and less costly if there is a system which learns these patterns that, when taken together, make up a human face, when learning that automatically. That's the idea of deep learning. And demonstrably possible, image analysis is one of the application domains that have been revolutionized by deep learning. And I believe that this success of deep learning methods in certain applications, such as image analysis, is what has made the field of deep learning so popular. And what is maybe interesting for us is to reason whether this idea of learning features automatically would also work when we think about economic data. Think about economic time series, for example. Time series of macroeconomic variables, GDP, unemployment rate, interest rates, you name it. Well, probably you have done many courses on time series analysis, or know at least a little bit about the field and how time series analysis would also, involve approaches that aim at detecting certain patterns in a time series, whether there is a trend, whether there is something like seasonality, whether there is something like a recurrent pattern or a structural break. Well, it would be just awesome if deep learning would work here as well and offer a way to learn these patterns in temporal data automatically. Well, according to my experience, the degree to which this really is possible is moderate, or it's yet to be seen. But as far as image data is concerned, clearly deep learning is a go-to approach, and all commercial systems that are around these days use deep learning. Same for textual data. And hence, deep learning is one of the biggest fields of AI these days, I would argue. And then us focusing on deep learning is what the course focuses on, AI. All right, well, one of my favorite tweets or examples when it comes to AI, I wanted to show you as well. This is a great way, a tweet from Matt Veloso to frame it. Difference between machine learning and AI. You are obviously well trained in machine learning, so difference being if it's written in Python, it's probably machine learning. If it's written in PowerPoint, it's probably AI. Very nice ways to put it. He got many retweets and likes for this post. That is to show that, well, when you hear about AI, or when people tell you something about AI, make sure you always take that with a grain of salt. When we talk about most, not all, but most of today's systems, they are built upon deep learning, which is, if you wish, another way of doing machine learning, and in that sense, something you already know a lot about. All right, we can then come to the course Logistics, and I will elaborate on course Logistics in the next video. Thanks for watching.